All right. So this is the continuation of last semester's class. So last semester you were in coding one. This is coding two. If you are just starting in the class now and you didn't come from the previous class, whether you transferred in or something like that, I do have all the videos, the lectures from last semester if you want to kind of catch yourself up maybe from the last couple of weeks of that class since we're picking up where we left off. I'll talk a little bit about where we're going here in a minute. Um, But let's see. So grading, same as last semester, 60% homework, 40% exams. There'll be two exams, midterm and final. If you do better on the final than you do on the midterm, I will replace your midterm exam grade, what you earned on the final. Not the other way around. You can't do good on the midterm, then phone it in. You got to show me that by the end of the semester, you've learned this crap, and then we can undo deficiencies from the midterm. Sound fair enough? All right. Just like last term, you're going to have a good amount of homework. Homework's going to become more and more time consuming, right? As we get larger and larger projects. I mean, you saw near the beginning, near the end of last term, we were up to 5 or 6 different source code files and stuff like that for our little dungeon crawler. But hopefully we're going to start filling in things with working with multi-threading, working with online APIs, some things that can be applied to all sorts of different things in industry, kind of hiding it inside of a little video game that we're writing. So you've heard me say it before. It's like uh, giving a dog medicine by hiding its medicine in its food. All right, so that's kind of our approach here. Okay. Um, so hopefully this all seems pretty fair. I know several of you took advantage of this midterm and final thing from last semester. I think we had one student who got like a 12% on the midterm and got a 98 on the final, ended up with an A in the class. Um, and there were several students who were in a kind of a similar boat that made a giant leap. And only a couple students that leaped the other direction, but you know, is what it is. All right, so questions about the grading or anything like that before we dive in. All right, in terms of attending class, I always open up a Zoom session. So you can, and the link, I sent out an email with the link this morning. It should also be up on Blackboard, but I'll confirm that. Um, but if you prefer to attend class via Zoom, I don't care. That's fine. Um, if you are someone who thinks you will pay better attention by coming to class in person than having Zoom open at home and being able to have Netflix playing here or going and making a grilled cheese or whatever, you're adults, so self-police, but you're always welcome to come to class in person. But if you prefer to be on Zoom, I don't care. I do record every lecture, so and I put them up on YouTube. I'll put the playlist link up on Blackboard today after I upload this first video. So videos are almost always up within, I don't know, probably an hour after class is over or something like that. However long it takes YouTube to finish processing them, I upload it right after class. If you don't see it by then, remind me because it's possible I got interrupted by a student or something and it's just sitting there on the open window and I forgot to upload it. Doesn't take me very long to do it. So if you are looking for the video, give me a nudge and I'll get it up there. Let's see. So you can attend however you want. Um, you're responsible for anything we do in class. So if you are an athlete or something like that and are going to miss some classes, I always have athletes that want to miss classes for practice and stuff. But look, you're adults. I don't care. You do you, but you're responsible for anything we do in class. I'm not going to give you extensions on assignments and stuff like that. You're choosing to be a student athlete, so you have to manage your time. That's an extra responsibility. All right, questions about any of that? Okay, so let's remind ourselves how we got to where we are right now. So let's just call this a recap. So last semester we started with C++. All right. Remember, we used an older language like C++ to make sure we got ourselves introduced to things like memory and pointers and hexadecimal values, things that can be kind of intimidating for beginning programmers because some of these newer languages hide a lot of those things from us. And as we work through this course, we're going to keep seeing more and more abstractions. So we started with C++, so we saw a lot of the memory addresses and stuff like that. Then we moved to Java. So we kind of introduced, we're going to say, up through basic objects, moved to Java when we created our own objects. And we will be moving to Unity Game Engine, which uses C# as the scripting language here, probably within 4 weeks or so. We're going to kind of cover the some more stuff in Java, especially with threads and things like that, because a lot of that stuff's hidden from us in game engines. But we're going to be continuing to build out our dungeon crawler game, stupid thing, whatever, moving to a game engine. So when all is said and done, you should have a pretty good background in programming. Remember from last semester, programming is the skill set. Let me get another slide here. Reminder. Programming is the skill set. The language does not matter. Remember, all humans solve problems by asking questions, remembering things, and repetition. Programming languages, 100% of programming languages will have facilities for emulating these things. So we have conditionals, if statements for asking questions. We have variables for remembering things. And we have loops, functions for repeating things. All right, so every single programming language you ever run into will have facilities for these things. So when you learn to program, you learn to solve the problems using the concept of asking a lot of questions, remembering stuff. So what things do I need to remember? I'm going to need a variable for all those things. What questions do I need to ask at various points in time so I know, do I do something or not do something? Do I do one thing or do I do another thing? Those are going to be conditionals. And then getting used to the syntax and things like that for loops and functions, but more importantly, when to use those types of things. All right, so once you become a programmer, moving from one language to another is not really a big deal. You could pull it off in a weekend, as long as you can write a hello world program and figure out how to do these 3 things in that language. You're probably 75% down the road. Then you'll just bump into kind of the niceties of some languages. Some languages do certain things a little bit better or cleaner than other languages. So then that just becomes, that's the why you chose that language for a project or over another one. If you're going to do web programming stuff, you might choose to use PHP because it has a lot of built-in stuff for web things, especially if you're going to use a MySQL database. PHP and MySQL were kind of created at the same time and they're built in terms of each other. So it's very convenient to talk to a database through PHP. So you might choose that for if you're making a dynamic website. If you are creating an online API or something like that, you'd probably use something like Node.js for creating those things. So, but all these are just programming languages. Anything with a .js on the end of it is based on JavaScript. So frankly, most languages that or most technologies you hear people throw around that aren't Java, C++, C#, or call it Swift, they're probably some form of JavaScript. JavaScript exists in all sorts of different little wrapping papers. All right, so That's why we keep switching languages up in here, is to kind of prove this to you, that as you become a better programmer and you start learning these new tools, you realize all these things are very related to each other. We purposely do not use Python as our first programming languages, even though a lot of places do choose Python as as a first language. Um, I think for the wrong reason. Python has a fairly low entry point. You can write things very concisely in it. It has a lot of like conveniences, shortcuts built into it, which is great. If you've been programming for a long time, you really appreciate those conveniences. But when you're learning to program, it's hiding so much stuff from you that you lose some of the ability to learn those fundamentals. That's why we purposely don't use Python. All right. We're trying to, I mean, I think I talked about it last term, uh, kind of prove this point of why a college education in computer science is better than like a boot camp. When you do one of these coding boot camps or something like that, hey, you can go get a good paying job, hold it down, all this stuff. It's not a waste of time, but it's only going to teach you how to solve, let's say, 80% of the problems. A theoretical background in computer science is going to let you solve that last 20% of the problems. But learning a language like Python first, because the goal is doing things rather than learning the process, is only going to keep you at that 80%. We have to understand what's under the hood, because ultimately all of us are trying to become the equivalent of car mechanics, right? We're computer mechanics, or we're slinging around zeros and ones, if you will. So we need to understand those things so that we can solve the more difficult problems. Eventually, you'll kind of find your favorite language that has a lot of the conveniences in it for the things you like doing. And then you'll appreciate all those bells and whistles. Like, I like an automatic transmission, so I can have my coffee cup in one hand and my other hand on the steering wheel. Well, if I have a stick shift, then that becomes problematic. I have to wear those beer helmets, right? With the straw, and then you get burn your lips, and it's a thing. All right. Questions about any of that before we dive back into some code? Okay, so rolling back to last semester, I'll go ahead and drag this down here. Because remember that time I tried to give you a homework assignment? Do finals week? Because your professor didn't know when finals were? Yeah, so if you remember, we were working on this dungeon crawler where we had started introducing this idea of inheritance and things like that. So we had a class called Player when we first wrote our little death match thing, where we would create multiple instances of Player and have them try to kill each other by doing random dice rolls, kind of basing this on Dungeons and Dragons and beating each other up. Then we decided, well, let's create two specialty versions of players. We created a fighter that's a little stronger and has more hit points, and then we created a wizard that maybe hits a little harder or something like that. I don't remember the exact differences we made between them, but we differentiated fighters and wizards from players. So this was inheritance. We learned about the hierarchy, the object-oriented hierarchy of any object-oriented language. Um, that is to say, all object-oriented languages at some top level have something called object. In Java, it's a capital O object. In C#, it's a lowercase o an object. But there's this top level class that's built into the language that acts as the core structure of anything that exists as an object in that language. And objects are the antithesis to our primitive types. So if you kind of remember this idea, languages have two primary components. That's probably let's call that a mediocre at best title. We have the idea of objects, and then we have the idea of primitive types. Let's call this type components. All right, so remind me, what are primitive types? Not what are the primitive types, but what are primitive types in general? If you had to give me a generic definition of a primitive type, go ahead. Okay, so things that are built into the language. Anything else? kind of one differentiating thing between primitive types and objects, because there's plenty of objects that are built into the language as well. So for instance, strings are built into the object language. We saw a couple other objects last semester, like the character class, that kind of stuff. Okay, so what differentiates an object from a primitive type? Go ahead. Okay. Well, so there's already a preset list of primitive types built into our language. So we have byte, short, int, long, float, double, Boolean. Call it that. All modern languages have some combination of these. We saw last semester that the newer version of C++ dropped the concept of a byte. It is back in Java because typically the byte concept is used for like data streaming. When you're moving things over the internet, like streaming on Netflix or whatever, typically things come in as compressed bytes. So it's not so much that the data size is that important there. It's just kind of what's the right kind of container to hold it, right? When you have leftovers, you pick kind of the right size container for your leftovers rather than just put everything in a big bucket, right? That type of thing. So let's go. Oh, I forgot a major primitive type here. What did I forget? Jar. Not strings. Strings are object types that behave like primitive types, which should tick you off as a beginning programmer since it's almost always the first object we learn about. The first object you learn about is the only object that has special cases. All other objects behave identically except strings. But that's the one we learn first because strings are pretty important. So primitive types, as she was pointing out, they're built into the language, and these we can't expand these. Okay, we can't create more primitive types. In older languages like C and C++, we did have something called enumerated types, where you can sort of kind of describe something as a new type that's based on an older type, but it's kind of a hack. It's not an important concept. So I think it's fair to say that primitive types, they're set, they're part of the language to begin with, and they don't change. All right. So what's the difference? So bytes, shorts, ints, longs, what do these guys have in common? What kind of values do those hold? Remind me. Okay, whole, signed, integer, values. What does signed mean? We say a value is a signed value. What does that mean? Can hold positive and negative numbers. All right. Now, as human beings, sure, numbers can be positive, numbers can be negative. Well, there's a consequence of being able to hold positive and negative values. It's a consequence of 1 bit. It's going to require 1 extra bit of your storage that you're giving up the ability to store a bigger number to store whether the number is positive or negative. Okay. All of you, or at least most of you, should be in the computer organization architecture class this semester, right? With Blade. You're not in that class? You should be in that class. Killing me. All right. If you're a computer science major, you should be in that class. If you're a different major like data analytics or something like that, you might not need that class. But in any case, you'll be talking a lot more about zeros and ones and those things, what's happening under the hood, because that class is about how do your computers actually store that kinds of stuff in hardware. All right. But believe me, all the different hardware storage locations inside your computer have a size of some power of 2. So, but these guys hold whole signed integer values. So they hold positive and negative integers. The way we store negative values is through something called 2's complement. You'll learn about that in the computer organization class. So we kind of encode negative numbers so that we can still do fast math, but get the positive or negativeness of a number out. All right. So that's what these values as a whole do. How do they differentiate? So what's the difference then between a byte, a short, an int, and a long if they all hold whole signed integer values? Good. Okay. So these guys differ in the size of values they can hold. So bytes can hold 8-bit values. So that's roughly plus or minus 2 to the 7th power, since we need one of those bits for the sign. All right, so that's negative 128 to positive 127. All right, so if you 2 to the 7th power, yay, is 128. Why do we only have, here, this would be a good, I probably mentioned it last semester. Why does an 8-bit value, like a byte, why does a byte hold negative 128 to positive 127? That's the range of values that can live inside of a byte. Why are those two numbers different? Why is one a 128 and the other one's a 127? Go ahead. Yeah, zero's in there. So we have 256 unique values that we can store in a byte. So an 8-bit value has 256 unique states, right? There's 256 unique ways of writing 8 zeros and ones. We can decide what each of those unique sets mean. In this case, we're using them to mean magnitude for a value, a numeric value. Okay, so we can represent 256 unique numbers with 8 bits. Since we've chosen to also be able to store negative numbers, we have to have a way of representing those negative numbers. So I mentioned that we use something called 2's complement to pull that off. That's not something we deal with in here. It's something you'll be learning about in the computer architecture class. But you're still stuck with, with 8 bits, you have 2 to the 8th power unique permutations of 8 bits. So we can hold 256 unique states, unique values. If we want to hold positive and negative values, we have 256 options. Why isn't it negative 127 to positive 127? Why is that number different? He's right. I think he actually probably knows the answer. What's a better way of explaining it? Good.
One of them, it's not like they don't,
How many ways do we need to represent 0? Do we need a positive and a negative 0? No. So there's something you'll learn about in the computer architecture class called 1's complement. It's the cheesy way of representing negative numbers, where all they do is they take that very far left bit, and it's a 0 for all the positive numbers, and it's a 1 for all the negative numbers, right? But what you end up with is 0 represented 2 times. 1 followed by 7 zeros, and 0 followed by 7 zeros, both equal negative 0 and positive 0. We don't need to, we just lost an extra number we could have represented, right? So we don't have to represent 0 2 different times. 2's complement allows us to encode the value so that we only have to represent a positive 0, and negative 0 doesn't actually exist, which then gives us an extra value on the negative side. That makes some sense? That's why we have negative 128 to positive 127. We're replacing negative 0 with negative 128 to get an extra value there. And this is consistent with the math. When you learn how this works with 2's complement, it's not like an exception type thing. The math works for this. So it really dictated it. That's so 2's complement is how we encode negative numbers, and it ensures we only get one version of 0. All right, so that's what a byte holds. What about a short? Shorts are 16-bit values. Go ahead. Pretty close. 768. So negative 32,768 to positive 32,767 for 65,536 unique values. 2 to the 16th power, as opposed to a byte, 2 to the 8th power has 256 unique permutations. If I have 16 zeros and ones, I have 65,536 unique permutations of 16 zeros and ones. I get to choose what they represent. So we've decided they're going to represent the numbers between negative 32,768 and positive 32,767. Then you get up to an int, ints are 32 bits, 2 to the 32nd unique representations. That's 4.2 billion-ish. I start losing my precision, right? 4.2 billion-ish, so it's negative 2.1 billion and some change to positive 2.1 billion and some change with one additional value on the negative side. You get up to longs. Longs are 64-bit, so that's plus or minus 2 to the 63rd power, since one of the bits is used for sign, which is what, like 9.1 quintillion or something like that, quadrillion. Big number, 2 to the 63rd, 2 to the 63rd power. All right. So those are our primitive types for our integer primitive types. What's a char? What kind of values do chars hold? But okay, from a human perspective, we expect a char, which is short for character, we expect it to hold A's and B's, characters, question marks, anything that's a symbol in the alphabet or something like that, right? But what do chars actually hold? Go ahead. Yeah, so tell me about ASCII.
Have like a number and then that like words to the letter or something.
Okay, so ASCII is a mapping table from a binary value. Well, actually, let's just say from a number to a character. What's the alternative to ASCII? What's the newfangled version of ASCII? Unicode. So we have Unicode. Same difference. ASCII is 8 bits. Actually, I think original ASCII is a 7-bit value, which is actually kind of stupid. But 8 bits is the full ASCII set, and Unicode is 16 bits. What does that mean? Why is Unicode better than ASCII? Go ahead. Yeah, there's more languages than just English, right? And even ASCII was pretty lazy with English because they started putting in smiley faces and playing cards and all sorts of crap. Back then, we didn't have graphics and things, so you had to make your software with those things. Yeah. They didn't exist. You would have had to create your own encoding mapping or something like that, and then you would have needed to have a terminal that was capable of displaying it. So even when you even if you're using Unicode now, if you're working with a terminal, like, here's like Unix terminal here, if you're working on this, this guy is probably, I think the default terminal is the UTF-8. Let me just. Yeah, UTF-8 is the default. So this is actually only 8-bit Unicode. This is a fancy way of saying ASCII, is what that effectively is. So this says select the encodings you want to appear in text encoding menus. This probably then also translates into what is supported out here. So for instance, even today, your question was just about what happened before Unicode, whatever. What I'm telling you is right now, if I put some, Greek letter in the Unicode value for some Greek letter right here, it won't display right on my terminal here until I click this little box to say, hey, learn how to do these guys too. Go ahead. Oh, let's see. Well, you had to ask that, didn't you? So these are a bunch of different flavors of Unicode. I'm guessing some of these would have, so when it gets to like Latin US, that's probably starting to be related to what she was asking about. This is from older DOS days when the stuff would have made a big difference when terminals didn't support the stuff. So that character set would have supported Latin characters, for example, but these were kind of like non-standard character sets. So ASCII became kind of our first standardized character set. American Standard Code for Information Interchange. Unicode became the, hey, we actually want to represent letters from other languages version of that. And then all these in between, you start getting into like the Japanese and traditional Chinese stuff. That's the terminal's ability to show the kanji characters and that kind of stuff. Good. A lot of times it'll be like a question mark or like a weird box looking thing. Yeah, it'll look like gibberish. Yeah, so if you've ever had like an executable file, let's see what I have in downloads here. Oh, here's that's a video of one of my fish eating another fish. It's on YouTube. It's awesome. I have Star Wars music to it and everything. There's lightsabers. It's a Oscar. So he's probably foot long or so now. I got him when he was like that big. So if I do that, so this is an MP4, it's a video file, and I'm going to try to show the contents of that video file in this terminal. So what is it trying to do? It's trying to, because that's a binary file, right? A bunch of zeros and ones are inside that file. This guy's trying to treat it as if it's ASCII text, a bunch of 8-bit characters. And it's getting all sorts of weird symbols and stuff because there's a whole bunch of stuff in there that I mean, it wasn't even necessarily divided up into 8-bit chunks. All right, so this is the output you get from something like that. So here's your question marks, and oh, here's some weird stuff. I always like when you get into those situations, like, how do I type that? Sometimes I'll want to type something that you can't figure out that the key sequence is too crazy. You just go to a web page that has it and you copy it and paste it in there and you're good. All right. All right. So Unicode, as she pointed out, supports more characters, i.e., more languages, symbols for more languages and things like that. All right. So what kinds of values actually live inside of a char? If we're dealing with C++, it's ASCII values. If we're dealing with Java and newer languages, it's Unicode values. Unicode's a superset of ASCII. So the first 256 Unicode values are the ASCII character set. And then you have the additional things. But chars hold, so we'll say 8-bit unsigned values in C++ and 16-bit unsigned values in Java/C#. Basically, all modern languages will be operating on Unicode now. But if you're only ever working with the English language, they're identical to you, except Unicode's more wasteful. It's going to waste an extra 8 bits in your char types. Okay, so what does it mean then? Why do chars hold unsigned values, whereas these integer types up here hold signed values? Because keep in mind that a 8-bit char is the same physical size as a byte. So why are chars unsigned? Go ahead. Well, we certainly could, but because we're operating off the ASCII and the Unicode set, if you go and look at those mappings, they start at 0. And they go all the way up to 255, which is 256 unique representations on the Unicode or the ASCII set. Or if you're looking at the Unicode table, it goes from 0 to 65,535 for 65,536 unique characters. Make sense? Okay. So we don't need to hold negative numbers. So that means we get to use the entire 8 bits or the entire 16 bits for holding the magnitude of the value, the number, because we don't need to represent sign. Nothing says that they couldn't have written the ASCII or the Unicode character set to go, or Unicode to go from negative 32,768 to positive 32,767, where maybe one of those umlauts or something like that in some other language was technically a negative number. That's what it mapped to. They could have done that, but that would have just been weird. Somebody designed it that way. It's like, I just want to kind of deal on the negative side for whatever reason, but that's not how they designed it. They designed it for 0 to whatever number it went to. So we don't need to hold negative numbers. So that's why chars are the same kind of value as ints, in that these are all just buckets of holding zeros and ones, but how we read them is different. Chars are read as unsigned, therefore we're just mapping it to the number that's on the Unicode or the ASCII set, whereas integer types like byte, short, ints, and longs, they hold signed values, so we do have to pass it through that filter of, hey, am I looking at a negative number? If I am, that means it started with a 1. I have to decode it to get the actual value. You decode a negative number that was encoded in 2's complement to get the value of the number, and then you just put a negative sign in front of it. 2's complement is you flip all the bits, add 1 to it. Gives you the 2's complement of something. So if you're going to undo the 2's complement, you got to reverse that process to get back to your original. And you'll learn about that in the architecture class. All right. What about floats and doubles? What are floats and doubles? What kind of values do these guys hold? Good. Yep. So signed decimal values. These are the integer types of floating point values. So just like byte, short, int, long hold different magnitudes of values, a float holds smaller maximum size values than a double does. So a float in most modern languages is 32 bits before the decimal point, and then 16 bits after the decimal point. For 48 total bits is the size of that space, whereas a double is 64 bits before the decimal point and 32 bits after the decimal point. So, that's the size of that guy for total size. What is interesting, just as a kind of what's common best practices or something, almost always in modern programming languages, if we want to hold a whole signed number, we put it inside of an int, even if the number is only going to be a number between 1 and 10. We're much more wasteful with memory today because we can be. Memory's not as big of a deal as it was back when these languages were first invented. So typically, if we want to hold a whole signed number, we use an int. If an int's not big enough, then we use a long. If we are working with floating point values, we typically actually use a double. Even though it takes up more space, it gives us more precision when doing math. And typically when we're using floating point values, we're probably doing, in like a game programming type thing, pretty high precise things. So those decimal points way out there might make a tiny bit of difference, maybe. Who knows? Interesting. How many of you have ever been, if you're into graphics cards, GPUs or anything like that, you see the difference between the consumer gamer graphics cards and like the graphics cards, like the Quattro graphics cards for the professional video people and things like that. And you wonder, why are those cards more expensive and why don't they do video games as well? Anybody know the difference between like the RTX consumer cards and the Quattro cards? Architecturally, they built the a graphics card is basically a floating point calculator. It has a bunch of cores in it, and all it does is do floating point math all day long. That's what it's good at. The Quattro has larger memory segments for the floating point to give it more decimal places, which gives you more precision when you're doing like video encoding and stuff like that, where if you're having a card that you're playing a video game on, I promise you, you're not realizing those last couple of decimal points running at 130 frames per second. I mean, it's not going to be a value add for you. But it is different. It's not just a like, oh, it's the same card at 3 times the price. There is a difference in how they build the chips. All right, so floats and doubles hold decimal point values. What about Booleans? Go ahead. True and falses. True and false. Old school, these were represented as zeros and ones. Modernly, you with like Java, C#, you can't actually get to the 0 and 1 with Boolean types. You could actually do math with Booleans in C++. Not that that ever makes sense, but you could. But anymore, they're represented as just a 0, well, represented as true or false, and under the hood, they're stored as a 0 or a 1. Some languages, instead of true and false, they represent them as yes and no, which I think is sort of kind of interesting, but it's not commonplace. But remember, every single one of these guys under the hood is just storing a number. They have some number of bits associated with it, and they're storing a number in those bits. And then depending on the type, that number may or may not get converted to something else, whether it's decoded, whether it's looked up on the ASCII chart or the Unicode chart. At the end of the day, it's just a number. So computers like numbers, human beings like a wider variety of things. What about objects? Getting back to that question of the difference between objects and primitive types. So primitive types built into the language, so we can't add any more of them. Anything else you can tell me about primitive types in terms of what differentiates them from objects? Go ahead. Well, memory does play a role in it. I mean, we've already seen that the memory associated with all these different primitive types is set in stone, right? A byte is always 8 bits. A int is always 32 bits. Now, what that ultimately tells us then, though, is that these primitive types can only hold a value. They're built with a very specific purpose in mind. That purpose is to hold whole signed values. In this case, a byte, a short, an int, a long is built to hold a single whole signed value of various sizes. A char is built to hold a single whole unsigned value of, depending on the language, either 8 bits or 16 bits. A float and a double or signed decimal point values, so on and so forth. But all they can do is hold a single value. Those values can change. I can say int a equals 7, and then the next line I could say a equals 13. I can overwrite the value that was stored in the 32 bits of that integer. But its only talent in the world is to hold a single value. What about objects? And what did we look at in C++ before we stumbled upon objects? What was our intermediary? We went from primitive types using those, and then we decided, hey, you know what? I might need to store more than just a single value. So what was our middle step? Well, tell me what. Good. I mean, glad you brought that up. What's a pointer?
It's just like the first thing, I think, you have like values that are stored with characters and all that. I guess what you can say,
Pointers hold memory addresses. Ints hold whole sign numbers. Pointers hold memory addresses. Depending on the operating system you're working with, whether it's a 32-bit operating system or a 64-bit operating system, that tells you how many unique memory addresses exist on the computer. Okay, starting to see a pattern here. These number of bits of things are always how many unique somethings can I represent? How we use those unique values is up to us. We're not always using it for counting, right? Sometimes we use it for Unicode, mapping or whatever. Okay, so a pointer holds a memory address, and typically memory addresses are used to represent unique places in your computer's memory that you want to store stuff so that you can get back to it later, right? We typically look at memory addresses as hexadecimal values instead of decimal values. Why is that? Give myself my 411, so that's a it's an 8 followed by a 0 followed by a 13, so that's an 8, 12, like that. What's the difference between those values? Go ahead. Third try, third. All right. So these all mean the same thing, right? If you want to think about this, this is in French, this is in English, this is in German. But they all mean the same thing. They all have an underlying numeric value they're representing. Why do we typically represent memory addresses in hexadecimal, base 16? Go ahead. That's it. Simple and concise. Memory addresses, there's a lot of them. Most of our modern operating systems are 64-bit operating systems, which means that there's 2 to the 64-bit unique memory addresses on that computer. 2 to the 64-bit unique places you can put stuff. Typically, 16 of those bits are used for kind of the operating system space. So really, from a user space perspective, there's 48 bits, which is still 2 to the 48th is that big number. It's that 1,000, million, billion, trillion, 281 trillion, 474 billion, 976,000. Oh, no, 976,710,656. So if you pretended like these are all little P.O. boxes at the post office, and you got to go and find out which box a certain thing is in, that's a lot of them, right? And if we wanted to count those in decimal, we would say, okay, well, this is box 0, box 1, box 2, box 281, blah, 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 blah. Okay, 281 trillion. That's a lot of boxes. So we can choose to represent that in a smaller footprint, which might mean we represent that as a hexadecimal number, which will mean the same thing, but it'll be more concisely written out. And remember, with 48 bits, how many bits does it take to represent every hextet? Remember, this is our trick. Call this the hex and octal tricks. So hexadecimal numbers are made up of things called hextets. Sextets. I guess that could have gone way worse. So hextets, these are for hexadecimal numbers, these are like the digits, but they're called hextets. So hextets are 4 bits. That's 0 to 15. That is 0 to 9, A through F. So 16 unique hextets. And we can represent them as 4-bit values, which is what I did right here. When I converted BAD from hexadecimal to binary, that's a B with 4 bits. That is the A with 4 bits. And that is the D with 4 bits. So you can do the mapping. Go ahead. 50. Oh, are you done? 3 minutes. Oh, that could have been worse. Oh, no worries. Thanks for letting me know. All right. So we'll stop there. We'll pick up from here. No homework yet. We're reviewing from last semester, so we'll keep trucking from there.